All right. So we stopped about the at the place where it was describing about the evolution from meteoritic evolution, right? So uh, for you can remember the age of the Earth, right? It's 4.5 billion years, right? It's somewhere here. Okay, about 4.5 billion years time. The planets were formed from meteorites, right? Asteroids or meteorites. Okay, right. Then, for a certain period of time, the planets were under evolution, right? We call man evolution. Actually, at that time, there was no mantle, or the entire magma ocean was there, right? Entire magma ocean was there, but little later, like say 100 million years time, 100 million years time after the formation, 100 million years after the formation, what happened was the core separated. Okay, the formation of the core. Until that time, it was a magma ocean. Until this time, it was only a magma ocean. Okay, until that time, it was a magma ocean, and then core separated, and it was called, the entire Earth was called bulk silicate Earth, because all the metallic elements were separated into the core. Okay, we call bulk silicate Earth because it was separated, the metallic elements were separated, and all the other silicate portion was remained. So in the metallic portion, what happened was the nickel iron enriched elements were concentrated. That's why we consider that point as the core separation, right? Just after 100 million years later. That means after 4.56 billion years. So you just subtract 100 million years there, and then that is the time where the core separation completed, right? It's not just started there, but just completed, right? It took about 100 million years for the core to be separated. That is the first stage of we call it differentiation, right? Differentiation of the Earth. Draw this diagram clearly. Okay. Then what happened? After some time, around like nearly close to 3 billion years time. Okay, it's not exactly, it's around 2.7 like, right? But it's debatable. There is no exact age, but between 3 to 2.7, right? We consider the bulk silicate earth, which was just composed of all the silicate portion of the earth, right? uh, Again differentiated into two two components, right? That's called the upper mantle and lower mantle. Upper mantle and lower mantle. Upper mantle and lower mantle, right? So at that time, okay, yeah, uh, almost actually you can't say that exactly this happened at 3. That's why I mentioned, because this may have started at around 3 GA and maybe continued like up to 2.7, sorry, up to 2.7 or something. And around 2.7 another process happened. I mean, during this process, this during this period, this bulk silicate earth was differentiated, making two components, upper mantle and lower mantle. And then um, after 2.7, maybe it started 2.7 because there are abundant evidence from rocks to consider that the second process, this 2.7 process, has happened later. This upper mantle again fraction or again differentiated into uh, uh, it started to form continental crust, right? It's not kind of a differentiation, but it's a melting process. Okay, it's a major melting process of the upper mantle. It started to form continental crust, right? So until the age of 2.7, like, right, at least no, at most 2.7. Okay, uh, until 2.7, we can assume that the bulk silicate earth was dominant within the earth, but some fractions of upper mantle and lower mantle was also there. Okay, so initially what we had was bulk silicate earth plus the core. Okay, and then gradually it started separating the upper mantle and lower mantle. Okay, so that means the bulk silicate earth itself was started to differentiate. Okay, so there was then upper mantle and lower mantle part plus the core, but majority of this area was still dominant with bulk silicate earth composition. Okay, bulk silicate earth composition, uh, which was carrying all the silicate materials. But later on, what happened? This upper mantle section, the upper mantle portion, started to melt and started to form the core. Sorry, started to form the crust. Okay, the crust, very thin crust, first appeared on top of on the surface of the earth, and we have a little upper mantle portion still, and then we have the core. Okay, so once this uh, crust, continental crust, started to form, uh, this bulk silicate earth material which were lying here was gradually pumping to the upper portion of the interior to make the upper mantle. Okay, so we have continental crust and then upper mantle, and then actually this part, although we consider it still as bulk silicate earth, we can call now it as the lower mantle portion. Okay, now the earth has lower mantle, upper mantle, and continental crust. Okay, these three layers were completed by the age of around 2.7, right? Sorry, not completed. It started to appear, started to form. Okay, the first continental crust formation started to for appear at 2.7. Some says it's 2.8, but we can't exactly put a limitation there, age limitation, but you can just consider 2.7 to 2.8 as the first step of continental crust formation. From there onward, it continued. Okay, even up to today, this continues, right? The thing is, the bulk silicate earth, the original bulk silicate earth that we considered before, later contributed to the upper mantle. Uh, Still, we can't say that it is of the bulk silicate earth composition, right? Even today, we can say this the most deep or the most interior part of the mantle is still within the bulk silicate earth composition. The reason is all present day formations like continental crust that I just mentioned is only a product of the upper part of the mantle. Okay, only upper part of the mantle contributes, or the upper mantle contributes to the formation of continental crust even today. Okay, so the interior, the most interior part, the pulsilicator, still uh, uh, assumed to be composed of original or the initial composition, which might not be exactly same as the meteoritic composition. Okay, because this came from here. Okay, this is the origin, the meteoritic composition, original composition. Okay, but we assume the composition is very close to the meteoritic composition, but slightly, probably slightly uh, changed, because with time it might have taken some processes with these all these mental differentiation processes. But still we can consider the bulk silicate earth composition is represented by this interior part of the mantle. That means the lower mantle composition can be approximated to bulk silicate earth composition even today. Okay, so even today you get very close composition to the bulk silicate earth composition if you analyze any mantle rock coming from the lower mantle region. Okay, but the thing is lower mantle is not easily accessible. That means the wherever the mantle rocks that we have in we mentioned the places where the mantle rocks are available, right? Remember, ophiolites, mantle xenoliths, orogenic pedrotite massifs, abyssal pedrotites, all these are mantle rocks, but they are not coming from the lower mantle. They are all coming from the upper mantle. Okay, lower mantle is deep, so it's not easy to get those samples, but there is one possibility for lower mantle sampling available. Can anybody tell me? I have mentioned it before, I think. Yes. Can anyone tell? You have the mic. How we get very deep mantle samples beyond the upper mantle levels? That means some thousands of kilometers deep. I mentioned some kind of magma is coming up. What is that? Quickly. No one can remember? Yes. Quickly, quickly. Until somebody says something, I don't continue. It can be correct or wrong. That's all right. Sorry, I didn't hear.
Composition is similar to mantle peridotite.
Yeah, I'm asking where we get. I mentioned the periodites are available in certain settings, right? Mental periodites are, that is the mental composition. That's correct. But I'm asking something else. I'm asking where we can get the lower mantle samples, because upper mantle samples everywhere we can get from mantle xenoliths, abyssal petrites, ophiolites, everything, right? But not the lower mantle samples, because it is deep. Lower mantle is deep. There is one possibility I have noted it before. From which type of magma it is coming up. For example, I just remind you, the MOB, mid-ocean ridge basalts, are coming from upper mantle, right? They are coming from, that's why they carry the xenoliths, petrotite xenoliths, small fragments of rocks, which is of the mantle composition. I ask you to read also, I mean, some texts. Somewhere there should be mentioning about this. What is this special type of magma which is coming from deep part? Can't you remember? Mantle plumes. Okay, they carry materials even from core mantle boundary, right? It has been evidence that plumes carry materials from core mantle boundary, right? So it is just about the core. It's coming from here. The plume is coming from here. This is core mantle boundary. Okay, it's very deep interior, so they carry some evidence for lower mantle composition. So those samples are approximately equal to the bulk silicate composition after analysis people have found. Okay, that means close to meteoritic or original uh, composition, this composition. Okay, right. So anyway, this evolution happened, right? This evolution from here to here happened, and at about 2.7 or 2.8 time, what happened was the continental crust was separated. Okay, that means mantle started to melt. Partial melting of the mantle started for the first time at around this age. So partial melting means, so the upper mantle, if you have this as the upper mantle portion, it produces a melt as a result of partial melting. Partial means it's not complete. So a melt is produced and the residue is remaining. Okay, so you have a residue and you have a melt produced. So this melt produced is coming up because it's light. So it contributes to the continental crust. So that makes up the continental crust gradually, little by little, building up. Okay. And the residue, the remaining residue, we call, because it is not the original upper mantle, because it has already contributed some melt. So therefore, this residue we call depleted mantle. Okay, the residue is the depleted mantle. We call it depleted mantle. So the most above, or the most exterior part of the upper mantle is called the depleted mantle, because it contributes to melting. So for example, if you take this as the upper the upper mantle, right? You take this as the upper mantle and it started to melt and formed some continental crust, and then what happened? It produced a residue. Actually, that residue, look at that residue, remains over here. Okay, at the extreme upper part of this upper mantle, extreme upper part of this upper mantle, right? Upper part of the upper mantle. Remember, this is upper mantle, and upper part of the upper mantle is this. Okay, and that is what you call the depleted mantle, right? So from the upper mantle also, there is a small layer called depleted upper mantle or depleted mantle. So because that layer is formed because of the removal of the partial melts, right? So below the upper part of the upper mantle, that means below the depleted mantle, still you have the normal upper mantle, right? After that, you have the lower mantle. Okay, so remember, at the top of our planet, we have crust, continental crust, and then you have the depleted mantle, right? And then you have the normal upper mantle, and then you have the lower mantle. Okay, then only you get to the core. So this is how the Earth's the differentiation took place. So this is what we call the whole process. We call the differentiation, Earth's differentiation. So you have to understand this very clearly, because otherwise, always the things get confused, because these ratios, isotope ratios, we are referring to different reservoirs. We call these reservoirs, mantle reservoirs, right? Upper mantle, lower mantle, bulk silicate earth, continental crust, all these things we call the reservoirs. Okay, mantle and crustal reservoirs. Okay, so now you know even the upper mantle, sorry, even the continental crust uh, has been divided into two portions, right? Upper crust, lower crust, right? Upper continental crust, lower continental crust, due to some later processes. So we will discuss about those things later on. But just for the time being, consider mantle depletion was caused by continental crust extraction, right? Continental crust extraction. We call it crustal extraction, has caused the upper mantle to deplete. Okay, so we can put this in different words in different ways, but the same meaning. Okay, the originally we had the bulk silicate earth, and then it was separated into upper mantle and lower mantle, and the upper mantle again started to melt, partially melting, and it contributed to the continental crust, and then the upper mantle, the uppermost portion, was only the contributory segment for the continental crust, which can be termed as the depleted mantle. Okay, so sometimes we term this as DM, or sometimes we call it DMM also. Sorry, not B. DMM also. Why do we call it DMM? Why we call it DMM? Depleted mantle DM is okay, but some people call it DMM. It's because in mid-ocean ridges, okay, in mid-ocean ridges, this is happening very extensively, right? This is happening very extensively because we can observe that in mid-ocean ridges means the divergent plate boundaries. Okay, there you have the asthenosphere here, partial melting takes place. This is a upper mantle, and this mantle contributes formation of the melt. Okay, so the melt, which is called MOB, mid-ocean ridge basalts, right? So this upper mantle forms mid-ocean ridge basalts. So therefore, people used to call uh, this mantle section, that means this section, this upper part of the upper mantle, that means the depleted mantle region. This depletion has taken place because of continental crust extraction previously. Okay, continental crust extracted, and because of that, you have this DM formed, depleted mantle formed. And this depleted mantle, again subject to partial melting, and forms mid-ocean ridge basalts, MOB, in divergent places or spreading centers. We call it spreading centers also because it's a divergence. Plates are moving away from each other, allowing the asthenospheric melts to come up. So since this MOB is performed by this mantle, by this upper mantle, people used to call it DMM also. That means depleted MOB mantle. Okay, DMM, depleted MOB mantle. This is also equivalent to the depleted mantle, because depleted mantle is everywhere in the upper portion of the upper mantle, but MOB is produced in spreading centers only. Okay, the mob can be observed in spreading centers only, because other places there is no way for the produced melt to come up, right? So you need this type of spreading, plate divergence. Otherwise, nothing can be come up through this space, right? So anyway, because of mob is produced by this depleted mantle, uh, people used to call it DMM, depleted mob mantle. Okay, so now we know uh, what the fractionation or the differentiation. Sorry, differentiation. Fractionation means elemental moving from one source to another, one place to another, right? Differentiation means the compositional variation happening as a process, as a geodynamic process, right? So until this point, this continental crust separation point, the mantle was evolving, right? Mantle was evolving, nothing happened, changing its isotopic composition. But because here a significant amount of material was removed, forming the continental crust, right? The continental crust was formed as a result of this process here. So that means your original mantle composition was considerably changed because of this continental crust formation, right? So a lot of elements were partitioned into this continental crust. Okay, this continental crustal producing magmas, right? So now our mantle, early mantle was depleted, as I mentioned. The very upper part of the mantle was forming the DM, depleted mantle, and this depleted mantle was evolving like this. Okay, because this material fractionation happened, so therefore a lot of elements were enriched in the continental crust magma. That means this magma. Okay, so we have now left with a very depleted portion of the mantle, and therefore a lot of strontium, rubidium, everything has gone into the this crustal segment, continental crustal segment. Therefore, the mantle existing mantle from that time was depleted. So therefore, it changed its direction towards a lower isotopic composition, right? So therefore, this evolution of the depleted mantle, that means we call rubidium depleted mantle, because in this case we are talking about rubidium strontium isotopic system, right? So rubidium, a lot of rubidium was fractionated, right? Elemental fractionation, that means moving of element. A lot of rubidium was fractionated into the continental crust forming magmas. Therefore, the original mantle was depleted. That means concentration was lower, and therefore it made a deviation like this, right? Downward deviation like that. Okay, so the evolution of the rubidium depleted mantle until today, until present day, is like this. Okay, it's going like this until today. So the continental crust evolution goes like this until today, because it was enriched with rubidium. So if you have a lot of rubidium fractionated at this stage, that means somewhere here, okay? And this rubidium over this large period of time, gradually, little by little, form lot of radiogenic strontium isotopes. So therefore, strontium isotope composition will go up in the continental crust. Therefore, you are deviating a line like this for the continental crust, increasing strontium isotopes. Whereas for the mantle, where it has depleted in rubidium, definitely the strontium isotopic composition will drop. It will drop down like this, right? Gradually, little by little, it will drop, right? That's why you have a trend like this. But for the crust, you have a trend like this, increase in trend, because a lot of rubidium was initially fractionated during this mantle melting time, and that rubidium converts into strontium as radiogenic decay continues, right? So this is the process happening, and this is why you have continental crust in very high amounts of strontium isotopes compared to the mantle isotopes, mantle sample. For example, if you consider this as a present day, today, right? You take this as the today. Okay, you take this as today, all right? So you have the mantle composition somewhere lying here, okay? Your mantle composition or isotopic composition may be close to, sorry, it should be a little above, because it should be not here, it should be here, right? Today's mantle composition is equivalent to this evolution line cutting the 0 MA age, and your continental crust, if we have a continental crust material, our isotopic composition, strontium isotopic composition should lie over here. So this is the continental crust uh, isotopic composition of strontium, and this is the upper mantle isotopic composition of strontium in the strontium isotopic diagram. Okay, so if we present day, if we sample a mantle, a mantle rock, you will get very close to this 0.70 something. No, sorry, I don't know this value. It should be, yeah, it should be somewhere around 7, 0.7. Okay, you should be getting that value. Whereas if you take a say a granitic sample or charnocite from the crust, you will end up with a value somewhere here greater than 0.71, greater than 0.71 definitely. Okay, because this is 0.45 or something, right? It should be getting somewhere there, right? Present day isotopic composition. So this is how the rubidium strontium isotopic evaluation of composition changes over the time. Okay, so always remember, you should know how to explain this graph or this diagram in terms of the differentiation process in the mantle, right? So you have the mantle evolution, and you know the processes that has taken place during this melting process in the mantle, and you should be able to describe uh, about the isotopic evolution of a present day rock that you sample from the crust or from the mantle. Okay, right? Do you have any questions? Is it clear? Because this picture, this overall picture, you should be very familiar, right? If you have a question, you can just ask me now. I hope I'm audible to you clearly. Am I? Do you hear me very well? Do you hear me very well? But I can't hear you. Something wrong with the mic? Check whether it is. Anyway, I can see that you can hear me.
So we can hear you.
Okay, okay. Yeah, I can hear you also. All right. Right. So now, just some additional thing. Now we know the mantle was evolving like that, and we can say the present day isotopic composition. And if you suppose you have a rock today, suppose you have a sample from the campus premises, maybe condylite or charnocite or whatever the sample, which is belonging to the crust, right? Which belongs to the crust. So if you want to know its composition 1,000 million years ago, right? You know today's composition because you can crush it and make a powder and do an isotopic analysis by using an ICP-MS or laser ablation or whatever the technique. And but you are interested in uh, finding out its isotopic composition 1,000 years ago, right? About 1,000 years ago. That means you are interested in its isotopic composition when it was here, right? When it was here in this line, right? So that is 1 billion years ago. That's 1 billion years ago, right? So how can you do that? Is it possible for you to do that? That means you want to know its isotopic composition of this 1 billion year evolution time. 1 million years, sorry, 1,000 million years evolution time, or 1 billion years. How can you do that? Any idea? With the present knowledge, I think if you're smart enough, you should be able to tell me. You know the present day isotopic composition, and you know the principle of uh, all the principles of this isotopic evolution. That means you know the equation, right? Rubidium strontium isotopic equation, you know, right? So that's enough for you to find out its isotopic composition 1,000 million years ago, just to interpret. Not just 1,000, even if it was there at the time of 3 billion years time when the continental crust first formed, even you should be able to find out, right? How can you do that? Can anybody tell me? Just tell me. I'm happy to hear it from you. Now I have given you the clues even. There are two ways. There are two ways. Okay. So at least one way you should be able to tell me. Remember, your composition might not exactly lie on this line itself, right? This is average composition. Remember, average crustal composition. So uh, place to place, there are some small deviations from the crust, because some places crust is composed majorly on with granites, or some places maybe a lot of charnokites, a lot of andesitic rocks, like that. So therefore, there can be some fluctuation, right? Some error. There is always associated error. I mean, there will be some fluctuation, right? So always this value may be changing little by little. I mean, plus or minus, there may be. It's kind of an envelope, actually. It would be an envelope, like the evolution, something like that, right? Okay, suppose your present day rock that you sampled has a composition lying somewhere here today, presently strontium isotopic composition, but you are interested in its composition at 1 GA, right? So at this age, so you should uh, find out at 1 GA how this rock was, what kind of an composition it had. How can you do that? Very simple way is there, but still it's okay just to get an idea, but not the exact isotopic composition. But still it is okay, but if you can tell me by just by looking at this diagram, you don't need to do any calculation. Very simple. And you should have drawn this diagram in a graph paper to be more precise, right? So then you can get a very close composition, because then you will draw it in a scale. Okay, how to do that? Oh, you have the initial composition here. Okay, it's given as the timing of the mantle separation of sorry, crustal separation, continental crustal separation, right? Assume that our rock started to evolve at that time. Along this, consistent with this continental evolution trajectory. Okay, so you have one point here, your initial composition you have here. Okay, and your present day composition is here, right? You measured it, present day composition, you measured it. So simply what do, you make a line, you make a sorry, it's not a line, you make a line. If you draw this in a graph paper, it will be better. And then you just draw a intersecting line here to make it 1 GA. So then you are here with the number. Okay, so this number should give you the exact the approximate, so not exact, approximate value of your uh, isotopic composition, strontium isotopic composition at 1 GA. That is the simplest way. Okay, but if you want to be more precise and accurate, then definitely you will have to go for the isotopic equation, right? This is it. So you have to use the isotopic equation, and then you need to know uh, some other parameters. You have to find some other parameters, and then you can get the initial isotopic composition at 1 GA. So at 1 GA isotopic composition means you can assume it is the initial isotopic composition during its evolution. Okay, during its evolution. So you can, because this is an unknown, so that is what you want to know, initial isotopic composition at 1 GA, right? That is the parameter you want to know. So measured means today's isotopic composition. That is it's a known factor. You measured it already with, and also you can measure the rubidium strontium isotopic composition also. This is also present day, right? Not any previous. Only thing is this is the previous thing, initial thing. That is the one that you want to know, right? So what about lambda? You know already. Lambda no. And what about t? That is an unknown. T means the age from this initial time to today, right? From initial time to today is the T. That is the definition of T. The time which has evolved. Okay. So you put T instead of T, you can put 1 GA, because you are interested in for a period of 1 GA, 1000 million years. Okay. So then T is also known. So everything is known. So you can calculate the unknown. Okay, so this is how we calculate the initial isotopic composition of a given rock, provided that you know the present day isotopic composition, right? So this is what we call back calculation of age back calculation, or back calculation of age, or in other words we call age correction, because sometimes some of our interpretations, in our interpretations we want to know the situation prevailed at that time, at an initial time. Okay, so we are interested in finding out the original isotopic composition. So therefore we will have some we may face some situations where we want to find out the age corrected isotopic ratio. So this is what you call the age corrected isotopic ratio determination. That means if that rock is 1 billion years old, right? So you might know that age from another method. Suppose you have zircons from that age, rock, right? So you can independently analyze zircon and get a direct age of that particular zircon, right? So that means it is the age of that particular rock. So then you can put that age into this equation and find out initial strontium isotopic composition, because for some geochemical interpretations, I think I mentioned that isotopic ratios are used as geochemical traces. That means to recognize previous processes, previous geodynamic processes, maybe to trace mantle melting, to trace mantle magma mixing, or crustal interactions, like those things. We will discuss in detail those things in the future. Okay, for such interpretations, we need these initial isotopic compositions. So these isotopic compositions can be calculated by the back calculation method. So for that, you can use the equation, the isotopic equation, and then the known age you can put there, and you can calculate the initial isotopic composition. Okay, right. So always remember this initial ratio, usually by definition, when you crystallize the rock, it has the ratio that has that has been prevailing there is called the initial isotopic composition. So it's no harm to find out the prevailing isotopic composition at 1000 million years ago in this particular case, right? If that rock exactly crystallized at 1000 million years ago, it should have acquired that isotopic composition at that time. Okay, so anyway, this is what we call the back calculation, age correction or back calculation, right? All right. So uh, this is how we use this equation, right? So always remember to find out any time, if you want to find out the initial isotopic ratio, you have to do this age correction, right? Age correction means you have to find out its present day isotopic composition. That means you have to know this one, and you need to know at what age you are expecting for this rock to be generated. Otherwise, we don't know. I mean, otherwise, how do we know at what age we have to consider, right? Therefore, you need to know the initial isotopic composition. But in the case of independent, or only if you are using this strontium isotopic ratio, in that case you don't know the age, right? If you don't have any zircon age or something, this t is also unknown, right? But in this particular example that I mentioned, we were interested in 1000 million years, therefore we put easily 1000 million years there, because we are interested in only 1000 million years evolution time. But who knows, this rock was derived at 1000 million years ago, right? So we don't know that, right? Therefore, it is also an unknown if we don't have any other secondary data available regarding the age. So therefore, we have to do some other technique, a graphical technique. That is why we arrange this age equation in such a way that it is represented as a equation of a straight line, right? Y equals mx plus c. So here you have the y, and you have the m, and you have the x, and you have the c here, right? So this is y equals mx plus c. So therefore, if you can plot this y and this x in a diagram, in a plot, in a Cartesian plane, then you are able to find out C and M both. C and M both means you can find out the initial isotopic composition as well as the age, unknown age t. Okay, so because all these y and x you can find out from today's samples. So you can analyze multiple samples so that you get multiple values for y and x. Therefore, you are able to find out enough values for this straight line to be fitted in the diagram plot. Okay, So this is the normal procedure we use in strontium rubidium technique. Okay, right. So if you consider a particular rock, right, which was derived from the mantle, okay, you think that it was derived from the mantle, and in mantle you had, suppose you had an isotopic composition of this amount 0.2, right? In the previous case, remember, the mantle isotopic composition is close to 702, right? That's why, because it is common, it is a known value, right? So you can consider mantle is having that value, okay? Right. So, but when a rock crystallized, different minerals will be crystallized in the rock, right? Because uh, it's it's from magma. Uh, maybe first to crystallize is olivine, and then pyroxene, then uh, OPX, CPX, like that, and then maybe spinel or something like that. So different minerals will crystallize at, I mean, not even, it doesn't matter, they crystallize at the same time interval, but the important point is amount of rubidium that can accommodate by each and every mineral is different, because we considered something called there is something called partition coefficients in minerals. Okay, so you have original melt which is produced from this mantle. Okay, and this melt, I will put it as M. So this melt makes, I mean, it crystallizes olivine, it crystallizes pyroxene, it crystallizes spinel or whatever, right? Like that, it will crystallize minerals. That is how you get another rock formed from this mantle melting. Okay, right. So for olivine, there is some amount or capacity that can bear the rubidium to up intake. Okay, for pyroxene, there is another capacity. For spinel, there is another capacity. Right? I'm explaining it in very general sense. Right? It's not the correct term to use. Not the capacity actually, but the partitioning. I'm talking about the partition. So amount of rubidium going into olivine, amount of rubidium going into pyroxene is different to each other, right? Amount of the particular element going into each of these elements will be different. All depends on the matter called partition coefficients. There is partition coefficient. This is dependent on the melt composition, this melt composition, and the fractionating mineral. What is the mineral that you are fractionating? Because they have different structures. That's a simple thing. So you have different minerals crystallized. That means the partition coefficients of these different minerals are different. They are when they are having contrasting numbers, values. So therefore, amount of rubidium that can accommodate will be different, right? So therefore, not only rubidium, strontium also. Therefore, in your crystallized mineral, for example, if this is the first mineral, I mean, not first mineral, one mineral, second mineral, three minerals. There are three minerals. Instead of names, I put 1, 2, 3. Okay. So in the mineral one, you have rubidium different amount than the two, and strontium also different, and number three, there will be further different amounts. So therefore, the rubidium strontium ratio in that mineral will be different from rubidium strontium ratio of the second mineral, and those two will be different from the third mineral. So therefore, remember, even though you have a particular strontium isotopic composition for the initial melt, for the initial magma, the crystallizing minerals will have different rubidium strontium ratios. So with these different rubidium strontium ratios, uh, if you have 5 minerals, they will have 5 different rubidium strontium ratios, because they are just distributed among themselves. the rubidium, original rubidium, which was prevailing or which was available in this mantle, was distributed among these three minerals in different ways. So therefore, your original rubidium strontium ratio will not be reflected by your each mineral newly crystallized there. But if you take the rock as a whole, that means the whole rock, if you take this as a whole, you will have the same strontium isotopic ratio for that particular rock, because the rubidium strontium will not be destroyed, and this rubidium strontium ratio should be reflected in the crystallized melt also. That is the reason. But since you have different rubidium strontium ratios for different minerals, with time, if this rock allowed to evolve, say 1,000 million years, say it was evolving, that means it after its crystallization, right? After this crystallization, we leave it alone to spend 1,000 million years. So what happened during this 1,000 million years time? Definitely this rubidium available in mineral 1. In mineral 1, you have some rubidium that will produce some radiogenic strontium, okay, over this 1,000 million years duration, okay, because radiogenic decay continues. Radiogenic decay continues. No one can stop that, okay. So mineral 1, which contains some amount of rubidium, will produce some amount of strontium, say strontium 1, and mineral 2 will contain another different amount of rubidium originally. So during these 1,000 million years, it will accumulate, it will produce different amount of strontium there, okay. The mineral 3 will also do the same. So you will have different strontium amounts produced during this 1,000 million years time. So that means your present day isotopic composition, if you measure, right, you will definitely have different uh, isotopic composition. That means this is the present day. Present day means I'm talking about 1,000 million years later. Okay, you suppose the present day is 1,000 million years later. You will have different amounts of strontium there. So that means in three minerals, you will have different strontium amounts measured after 1,000 million years time. Okay, so you have different amounts of strontium produced. That means if you plot that in a diagram, you will have different amount of strontium in this. Some, I don't know whether it is 1 is low or 2 is high or whatever, right? We don't know until we measure it, right? 1, 2, 3 amounts which are different from each other. That is the point, okay. But originally this rock contained some strontium ratio which is equivalent to this value, okay. Originally it had 0.702, because that is the parent or the protolith, original material that produced these minerals. But each and every mineral now contains different amount of strontium ratios, isotopic ratios, because of this original difference in elemental rubidium differences. So that means mass of rubidium is different in each of these minerals. So therefore, these minerals will produce different isotopic ratios as a result of their original amount of uh, rubidium strontium ratios. Do you understand that? That means each and every mineral will evolve its own way, uh, producing a different amount of strontium isotopes in the producing rock. So if this rock was allowed to be there until today, right? So that means until today means present day today. So maybe suppose 3,000 million years later, right? Until today. So then still it will have further increased amount of strontium with time, because this is the this is the amount you had in the 1,000 million years time, right? This is the amount, but after another 2,000 million years later, that is today, if we think present day 0 MA, you will have increased, more and more increased strontium produced, because rubidium decays more and more. But you know the half-life is very large, so that means it does not finish their original amounts, rubidium amounts. To make it half of its budget, it takes some gigaannums, some billions of years to make it, right? You remember the half-life of rubidium? I think we mentioned it before. So therefore, still they can produce enough strontium so that you will end up with a higher strontium isotopic value in the present day composition. Okay, right. So this is a very important factor that you have to consider uh, during this during this the geological process where isotopic decay is happening. Okay, right. Anybody didn't understand anything? You can just ask me a question. Okay, anybody has any question? Sure, crystal clear. Again, I remind you, you have to read. Okay, you have to read the first rubidium strontium isotopic decay system in a textbook, right? So that you will digest everything very clearly, and it will help you to go to the next step. That is where we will be discussing about samarium neodymium isotopic composition. Okay, which is opposite. It has an opposite behavior to the strontium system. So therefore, you need to understand strontium behavior, rubidium strontium behavior very well, and then you can go for the you can proceed for the samarium neodymium system. Okay, right. So this is how its evolution is taking place, and now let's see how we can show this in a diagram, in a evolution diagram. Okay. So remember, we are going to make an isochron diagram. So isochron diagram means, I think I explained it before, uh, the isotopic compositions lying on a given time, right? For example, if we draw an isotopic isochron diagram using present day isotopic signatures, that means we are displaying how today these isotopic ratios are displayed by each and every rock after evolution of a maybe some 1,000 million years time. Okay, so that means if we are considering a core-genetic suit, that means the suit core-genetic means they formed from a single source. Okay, this one, for example. So this is one source. They produced all these three minerals, right? All these three minerals were produced from one single source. Therefore, for these three minerals, we can say that they are produced from a core-genetic suit. So we can, in other words, we can say these three minerals are core-genetic. Okay, these three minerals are core-genetic. That means they were produced from one same protolith, one same parent body. Okay, and also during this time interval, right? During this time interval, you should not have anything gained or anything lost from the system. So this is the basic assumption for this age equation, right? If you have uh, happened any kind of, if you have faced any kind of interaction which has caused these isotopic uh, uh, or these elements to be removed from the system, or some other elements to be gained into the system, this isotopic equation is no longer valid. So that means even for a metamorphic rock, it's okay if the metamorphism alone is there, because the metamorphism itself is a closed system process. Nothing happens in out exchanges. But if there is anything happens like metasomatism, right? That means external melt has come and interacted with these rocks and changed its composition, then these elements have gained something from those melt, or it has released something into that melt. So that means the no longer open system behavior is there. Even for metamorphic rocks, if it is extensively partially melted, right, for example migmatites, right, might not be suitable for isotopic determinations unless you consider some of their portions correctly. That means you have to, if you see a lot of melt produced, and in that case, if that migmatite, just a minute, disconnected. Okay, right. If you are considering any migmatite in, as I mentioned in the previous example, you have to make representative sampling. Otherwise, you are biased. So you might not be looking at the correct rock, right? That's why the representative sampling is very, very important. Correct sampling is very, very important. Okay, right. So let's see how we can show that rubidium strontium isochron diagram. Originally, let's imagine you have that rock, and we are now, remember, we are now considering x, y variation. I mean, the x and y. These are the two variables that we take for x and y, right? You have it here, x, y, and if we take an isochron, that means the minerals or the rock samples whose isotopic composition should lie on a single line. This is the representation of that line uh, of this equation, right? So there we have the intercept, that is b. That means here, okay, we should have the initial isotopic composition, and by the slope we must have its gradient, right? M. You can calculate the gradient. As you can see, this angle should represent the gradient, right? Tan theta. You can take the tan theta directly. You can measure it even using a protractor. It's very easy. So you should be able to draw this diagram. I mean, it's not a deliberate drawing. What you do is you measure the isotopic composition of different samples and just plot it and check whether it goes through a straight line, right? Your plot may be like this. Your present day isotopic composition, you take multiple samples, maybe 10, 15, 20, any number of samples greater than 3, right? At least 3 you must have, right? But the higher the better, because you get a very reasonable line. So once you get this plot, what you have to do is you can do the regression, right? Regressing, and you can find out the regression line, and this line should reflect this isochron, right? So you can extend it further so that it hits the y-axis, where you can find out the initial isotopic ratio. Okay, and you can measure the gradient of this line you draw, and find out this gradient is equal to E lambda t minus 1, right? So you can equalize it, and simply you can remove the E term by using log natural logarithm, and then find out T. Okay, so this is how you can easily calculate the age of a sample by using this strontium, rubidium strontium isochrone. Okay, so we'll see the initially you have some sample with some initial ratio, right? Some initial ratio. For example, like here, right? Just we'll take these three samples here. The original source was having 0.702 composition. That means the source must be equivalent to all these three minerals because they were produced from its parent, right? So that is the initial isotopic composition. So initial isotopic composition of all the three minerals will be same. Okay, all the three isotopic composition, the ratios will be same, but since they have different amounts of rubidium and strontium, right? Different amount of rubidium and strontium, they are supposed to produce different rubidium strontium isotopic ratios. Okay, different amounts of rubidium and strontium there. So therefore, if you measure rubidium and strontium ratio here, right? This one, because you need to know rubidium strontium ratio to measure this strontium, this rubidium 87 to strontium 86 ratio. Okay, actually there is a what you call there is a equation for that also. From rubidium and strontium ratio, how to calculate the rubidium strontium initial ratio. This can be calculated also, right? You can measure it using the mass spectrometer also, but we are normally don't, we are not measuring this rubidium strontium isotope ratio using the mass spectrometer. Instead, we use an equation. There is a factor to be used, because even though you use mass spectrometer, you get the same ratio. So therefore, there is no but I don't want to make you complicated, because at this stage you don't need to worry about how you end up with this rubidium strontium ratio, right? You just think for the time being, you measure this today, because we consider it measuring, right? We measure it and we measure these two, and then we do the initial ratio determination as well as age determination, right? But actually there is a formula, because there is a continuous variation of this rubidium strontium isotopic ratio with respect to some factor. Okay, this factor is a constant. So whatever the rubidium strontium ratios you have in different minerals can be multiplied by this common factor, right? And that will give you this rubidium strontium ratio in the rock, in the mineral you are concerned, right? But don't worry, you just consider, because this is present day today, what you observe, this is present day, not initial anything, right? Therefore you think that you get the rubidium strontium ratio also from the mass spectrometer. It doesn't matter, right? But the point you need to understand is, since you have different amounts of rubidium and strontium ratios, elemental ratios in different minerals, they will definitely end up with a different value of rubidium strontium ratio, right? You understand that? Even though you measure it by the mass spectrometer, or even though you determine it by a calculation method, right? Because this is constant, so this is variable for three minerals, so therefore you will definitely end up with three different uh, rubidium strontium ratios. Okay, so that's why when you plot that in the isochrone diagram, you will end up with different values. So for example, this is one mineral. You can consider one previous mineral. This is another mineral, right? So one mineral might have lower rubidium strontium ratio. The other mineral might have higher rubidium strontium ratios. Okay, so therefore you will end up with different rubidium strontium values, right? I think you can understand, you can remember that because you have different values. So this may be having lower value, this 0.8, but this may be having higher value because it's 1.2. So therefore it will correspond to two places in the diagram. Okay, two places in the diagram, right? But their initial ratios are constant. So therefore they all should lie along this line. Okay, along this line, because their initial ratios are constant because they were produced from a one parent. Okay, so after some time later, right? Suppose 20 billion years, according to this diagram, right? This says 20 billion years. T 20 billion years. Look here, 20 billion years, right? So after 20 billion years of time elapsing, what will happen for this system? The sample had this one sample had this ratio, obedience strontium ratio, right? What will happen? Radiogenic decay continues, right? In these two samples here, in these two samples, radiogenic decay continues. That means rubidium will decay into strontium. Rubidium will decay into strontium. That is the radiogenic decay. That is natural process. So throughout this 20 billion years time, this must have happened. Okay, so rubidium decays means rubidium is gone away, right? It is getting reduced, its mass getting reduced. So number of rubidium uh, atoms, atoms will be reducing, right? Gradually reducing throughout the 20 million years time. Instead, what is happening? Number of strontium atoms will be increasing because of this rubidium strontium radiogenic decay. This is the parent, this is the daughter. So parent is getting reduced, the daughter is getting increased, right? So if it has elapsed a half life, for example, you will definitely have a 50% of rubidium remaining compared to the initial time, and you will definitely have 50% of increase of strontium within the system, right? That happens. So you are reducing rubidium means you are reducing this ratio also, isn't it? Because this ratio is determined by rubidium strontium amount. This is determined by rubidium strontium amount, but this 86 strontium is a constant, right? Because it is stable isotope. I said it's a stable isotope. It does not change there, right? That's why we take it as the denominator. It is a constant matter, but only changing is 87. Is 87, right? So if you are reducing the number of atoms of rubidium, that means you are reducing the rubidium strontium ratio also, because you can remember the rubidium strontium isotope ratio is equal to this rubidium strontium value into F, or it is determined by this equation, right? So if you are reducing rubidium means definitely you are reducing this ratio also, right? So therefore, in your diagram, what will happen? Your for this sample, your rubidium strontium ratio will be reducing over the time, and instead you are increasing strontium atoms. That means you are increasing this strontium production also, right? You are increasing this strontium production. That means your ratio should go up. Strontium ratio should go up. So x-axis reduces, y-axis increases. That means your variation should be a direction like this. Okay. So during this 20 billion years time, your isotopic point, which was lying here, should be could be replotted to somewhere here after 20 billion years time. So after 20 billion years time, you will have a high strontium value but low rubidium isotope ratio. Okay. The same thing will apply for the other sample also, and this will fall somewhere here. If these two minerals were cogenetic, right? That's why our requirement was also, right? If they were two cogenetic, this isotopic variation, this isotopic change will be very, very parallel. Okay, these two will be parallel. That means their change of rate of change will be same for the two minerals if they were cogenetic. If they were cogenetic means if they were having same initial isotopic composition as here. Okay, so in that case, if they are having like that, then what you can do is you can draw a line passing these two mineral grains after 20 billion years time. So this is what the isochron that you are producing after 20 billion years later. Okay, so this is the isochron line you produce after 20 billion years time. So this is the reason for those two minerals to lie on the same given line. Okay, so they should lie on a same line means they should have same age. In other words, they should have same age. That means uh, this angle, this gradient, this tan theta. Okay, this theta angle, tan theta m should be determining their age. Understand? Okay, this is what you refer as an isochron. So this is the isochron you are getting after some time. So isochron means iso means same. Chron means they lie on a single line, right? Crons, thermochrons. If it is temperature, you can term it thermochron. That means equal temperature line. Here, isochron means equal age line. So you have an equal age line here for the two given samples. Okay, so by this line, once you construct it, definitely you can join only these 2 points because you know only these two values, but you can extend it up to its y-axis crossing point, right? Ideally, it should be equivalent with the initial isotopic ratio. If you did everything correctly, these two must coincide, these initial 2 points. Okay, if the system has behaved openly, if something has gained or something has lost, then definitely you will have a shift here. Okay, definitely you will have a shift here. That means you cannot call it isochron any longer. Okay, but if these are coinciding, that means your initial isotopic composition is correct. You are getting the extrapolation for the initial isotopic composition by using the present day isotopic composition. So your isochron must uh, intersect with the y-axis at a value which is equivalent to the initial isotopic composition, which is given here. Okay, is it clear? Is it clear? Okay, right. So you get an isochron here. So we'll see an example. There is one example given for bushveld, some granitic rocks. You know bushveld complex? It's in Africa. It's a very famous complex. There are a lot of rocks associations, including mantle rocks. And there are a lot of gold deposits, chromite deposits, many banded formations, very ancient rocks are there. Okay, so it's an example. There, people have determined present-day isotopic compositions of three granites, probably. I mean, three samples from one granite, maybe. It's not given the details, but anyway, cogenetic samples, right? They are supposed to be cogenetic. So once they get the value like this, for example, maybe isotopic composition, then you can regress it to get the line, right? The most approximate line can be taken by linear regression. All right, so that line is here, and measure the gradient of that. That means e lambda t minus 1, and by that they have calculated the age, 2.3 billion years of that samples. So what they measure is only rubidium, strontium present day, strontium present day, right? And then just plot, draw the line, and get the gradient and find out the age. And initial composition can also be taken if you extend this line to the y-axis crossing place. So this is an example. Okay, so for any rock that if you have, for example, you are sampling some rocks in your research project, then if you have a facility to find out the strontium rubidium ratios, then definitely you can find out its age and also the initial isotopic composition of the time of its formation. Okay, did you understand clearly? Because this is very important if we are to go further. Okay, right now let's see another application of this. Actually, this is more than an age tool, right? I think I mentioned it before also. Just not only for determination of age, we use these isotopic signatures. I mentioned we can use how these isotopic ratios are changing through time, right? Not only initial isotopic ratio, but also the present day isotopic ratio. But if you are suspecting any interaction in any of mantle or crustal process has affected your samples at say suppose 500 million years ago, we know that 550 million years ago the metamorphism has taken place in our terrains. So definitely this metamorphism changes this isotopic evolution. We call it resetting, right? Resetting of the clock. We say resetting of the clock because once a major change has happened, you can no longer use that isotopic system to trace the age, because for example, if nothing happened in this case, this bush shell complex, for example, right? Throughout this 2.3 billion years, if nothing happened geologically, I mean, if no metamorphism, nothing happened there, you will get this correct initial ratios and correct age. But in case if a strong metamorphism has happened in between, say about 1,000 million years ago, right? So then definitely your isochron will be having a different slope. That means your strontium, rubidium will be reset. Okay, their values will be reset. That means they will not show the continuous evolution like here. Continuous evolution that you show here will not be displayed, right? This type of continuous evolution will be affected. That means it will no longer uh, evolving like this, right? This metamorphism will affect. So that means we call it resetting the clock. That means that clock you can no longer use for time determination. It's something like you lost your battery in your phone, sorry, in your watch, and you replace it with a new battery. But even if it starts to work, do you do you see the correct time? No, you have to change the time because it has already reset, right? So something like that happens for the isotopic system also, because for these isotopic systems we call it a clock, because we are determining a time, right? So any metamorphic process will change this isotopic or the isochrone, right? Gradient. So in that case, you will get finally the metamorphic age from this new gradient. That means the latest resetting event up to that age you will get from this changed isochrone. Okay, so you will get a younger age. That means you will get a metamorphic age. Even for our metamorphic rocks, most of the time, if you analyze rubidium strontium isotope, you will end up with the metamorphic age like here, not the original age like this, right? So that is very, very important. If unless you have mineral separations, some minerals may not have affect. May not have been affected by this later process. Then they will represent the real gradient of the initial composition. Otherwise, they will have a separate gradient. Right. That is another point that you want to keep in mind. Okay. So anyway, uh, so we talked that we can use these isotopic ratios not only just for age determination, but for uh, tracking or tracing some geological processes also. We will see such applications later on. Right? But here I want to show you the initial, the original isotopic compositions of meteoritic materials, right? So it's called Barbie, basaltic and achondrite best initial. So this is the one used for uh, the initial isotopic determination of the Earth, which is the best ratio determined one. That's why it's called basaltic chondrite based initial, because several meteorites, actually these are chondrite materials, right, have been used from different places, discovered from different places, and their isotopic composition has been plotted, right? Then they give an isochrone like this. Okay, so this isochrone will give some initial value here and also an age like here. So 4.3.9 plus or minus 0.26 billion years. So what is the age of the Earth? 4.56, right? So you can add this error uncertainty also to this 39. So it comes up 555 or something, right? So that's why it's termed as the best set of meteorites. So this set of meteorites have been used in using the strontium rubidium systematics to find out the initial isotopic composition of the Earth. So that will reflect the undifferentiated Earth's isotopic initial, the bulk Earth's isotopic initial. I think you can remember this morning we talked about the Earth's differentiation, right? So originally Earth was having the bulk Earth composition, right? That means just after the core was separated, right? All the silicate portion was remaining there. So that is very, very equivalent to the meteoritic or the chondritic isotopic composition. So bulk Earth should represent this ratio, very close to this ratio. That means, and also we reminded that the lower mantle still we can call uh, very close to the bulk Earth isotopic composition. Do you remember I mentioned, right? Because upper mantle has changed now. Upper mantle has produced the continental crust. It has changed its composition. Therefore, you can't no longer consider the upper mantle is also equal to the bulk earth, but lower mantle has affected very limited variation except for this plume magma, which is coming from the core mantle region. But overall, lower mantle is very close to the bulk earth composition. Okay, so if you analyze flume sample, flume magma coming from this lower mantle region, you must get an isotopic value very close to this value. Okay, very close to this value because it is more or less approximated to the bulk earth composition, right? But you can compare this meteorite isotopic composition that is given here, 0.699, right? 0.699 here, you have it, and you compare it with most of the terrestrial rocks, right? Mid-ocean ridge basalts, which are products of the upper mantle melting. Their composition is 0.7025, and continental granites or the continental crust values, that is more higher, 0.7119, the strontium isotopic composition. I mean, if we plot these rocks in this diagram, right, they will plot somewhere here, right? Some values they will be plotting somewhere here above the meteoritic isotopic line. Okay, that's the point. And if you have ocean islands, you will have isotopic composition still above, but you see the value here. What is the value? Look, this ocean islands isotopic ratio, strontium isotopic ratio, it's given as how much? 0.07, no, 0.704. Okay, it's something like that. So can you approximate that to this one? Yeah, a little bit closer, isn't it? Little bit closer, not exactly, but little bit closer. That's why I mentioned you. If you find out lower mantle sample, it might give you approximate value to the chondritic values, meteoritic values. So these ocean islands means they are products of plume magmas, plume basalts, right? Plume magmas. That means they are coming from very deep, low core mantle region. That's why they are giving you an approximately closer value to the meteoritic isotopic value. Okay, so all the other samples which are found as a result of interaction with the upper part of the mantle, that means upper mantle or depleted mantle, right? They have different different values. Okay. So for example, this mob, you can argue that this mob is also having zero value, right? Even below value, right? It is because of another reason, right? It's not exactly because of they are produced from lower mantle or anything. Okay, remember. So therefore, don't go for comparison that with exactly with these meteoritic values. But the thing is, the mob mantle means that part is extensively being melted, and because of this melting extraction, a lot of rubidium has gone away to the continental crust. Okay, this continental crust has taken up many of the rubidium there. So therefore, the original rubidium available in the mob source region, the source region for this mob magma, is depleted. That is the depleted mantle. That's why it is giving this lower value here, and not because of any original signature. Right? It's a kind of an artifact. Right? It's not the original signature. Don't get confused with that, right? But these ocean islands have nothing to do with any crustal production or anything. They show you exactly the very close amounts to the primitive or the bulk silicate earth. I think I forgot to mention this bulk earth is also called primitive mantle, right? Another term is there, primitive mantle. Primitive mantle means the originally prevailed mantle, primitive, the first mantle after core separation. Okay, but overall, if you consider these values, what do you observe? See here, some questions given. Some questions are given here. Why are all present day strontium values greater than Barbie? Why they are greater than this value? Right? Why are they greater than the original meteoritic value? Can you tell? And also another one, why continental values are highest? Why the continental values are the highest? Why the continental values are the highest strontium in terms of strontium ratios? Why is that? Because this original meteoritic composition mantle has fractionated, right? It has differentiated. That means original mantle composition differentiated, forming the upper mantle and lower mantle. Remember, we mentioned about this before. Upper mantle and lower mantle. Okay, so most of these rocks, mob, Indo-Ocean ridge basalts, and other even ocean island basalts, they are produced after the differentiated mantle, not the bulk silicate earth. Okay, bulk silicate earth was before this fractionation, before this differentiation. Okay, so therefore, rubidium is a very highly incompatible element. Remember, a highly incompatible element. So therefore, whenever a melt or something is produced during this uh, differentiation, rubidium goes into that section, depleting the original source. So therefore, bulk silicate earth is the original source, which is giving an equal value to the meteoritic composition. But later products all are fractionated. Therefore, they have relatively higher amount of rubidium there. Therefore, they will produce more and more strontium. So therefore, they will definitely have higher strontium values compared to the meteoritic values. And the second question, why the continental values are the highest? Continental crust is the ultimate product of upper mantle melting. So that means they will further enrich a lot of rubidium there in the continental crust. Therefore, a lot of rubidium will be accumulated in the continental materials. That means a lot of strontium will be produced there as strontium 87 to 86. Okay, so that is happening there, and you will clearly understand why these values are showing this type of a contrast. Okay, so these are two important points that you have to keep in mind. So remember this change. For example, mob now shows 0.7025 or something, continent 0.7119 or something. These are average values anyway, and ocean islands this much, but the meteorites 0.699. So remember, this is after the evolution of our Earth, right? That means after T of 4.5 billion years, right? This is after this age, after 4.5 billion years age time. Our rocks are showing these values. Okay. So the bulk earth we consider as undifferentiated, right? So we call undifferentiated, and our terrestrial rocks we call differentiated. So for this undifferentiated to differentiated position, it has subjected to so many geological processes during this 4.5 billion years time. All right. So this is the content that I have to share today. If you have any question, you can ask me now. We have few minutes. Do you have any question? If you didn't understand anything, so I'm reminding you again, you have to read. Okay, don't just browse the Google and try to see uh, the contents, but you systematically start reading chapter by chapter. Right? I have already given you the textbooks, and also I have uploaded the course detail form in the Google Classroom. You can refer that for that recommended texts, right? At least three books, at least I think three books are there, right? Yeah. Okay. So we will end up for today's class, and we'll meet next time. Don't forget the attendance.